friends, welcome to Net Chemistry. Today I am going to tell about organometallic chemistry. You can see in your CSIR syllabus, it is a very important topic about inorganic chemistry. You can easily answer all the questions whatever they are asking from organometallic chemistry, right? Minimum 2 questions they will ask from this section, and it is a very easy topic. So everyone should learn this topic so that easily you can score you can answer 2 questions minimum. Okay, so let us start with the organometallic chemistry. Before starting into the organometallic chemistry, I want you people to learn all the D block elements completely and thoroughly. If you are finding difficulty in by hearting that D block elements, what you can do, you can keep some code word like this. See, scandium, yttrium, lanthanum. If you are writing, you can make some name or something which is easy for you to remember. Titanium, zirconium, hafnium. If you are not able to understand, if you are not able to by heart all those series like that, take some name in your own way. You can make a code word and you can remember that series. Vanadium, niobium, tantalum, chromium, molybdenum, tungsten, manganese, technetium, rhenium, iron, ruthenium, osmium, cobalt, rhodium, iridium, then nickel, palladium, platinum, copper, silver, gold, right? Zinc, cadmium, mercury. This is what D block elements. You should know first the D block elements and electronic configuration. And so first one is, this is 3D series, right? This is 3D and this is 4D series and this is the 5D series, right? This is the D block elements. Okay, here what is the electronic configuration? 4s2 3d1, right? 3d1 3d2 3d3, and here chromium, molybdenum, tungsten. If you are taking D4, actually it has to come because half-filled electrons will give you extra stability. So what will happen? It will become 3d5, right? 4s1 3d5 it will become, instead of 4s2 it will become 4s1 3d5. Then manganese, technetium, rhenium, if you are taking again 3d5 only, 3d6, d7, D8, right? Here copper, silver, gold, if you are taking copper, silver, gold, that also 3D9 it has to be. Then 3D10 will give completely filled orbital, will give extraordinary stability, so it will become 3D10, and zinc, cadmium, mercury 3D10, right? I am writing only first electronic configuration. Okay, here if you are filling it, it has to be 4D and here it will be 5D. Okay, this is the electronic configuration of D block elements. Now what is organometallic compounds? Your metal has bonded with a pi acid ligand, we will say. What is pi acid ligand? We will see first. Metal and pi acid ligand, this is what organometallic compound. Okay, what is a pi acid ligand? I am taking directly an example and explaining. If you consider the case of example, I am taking a carbonyl. Carbonyl means 6 plus 8 electron, right? 14 electrons are there. What is the electronic configuration of this? Sigma 1s2, this molecule I am writing sigma 1s2, sigma star 1s2, right? Sigma 2s2, sigma star 2s2. If it is up to 14 electron, you have to first fill pi orbital, right? Pi 2p x2, pi 2p y2, right? Then it will be sigma 2p z2, right? Then after that only pi star 2p x 0, pi star 2p y0, right? This is the electronic configuration of this CO. What is the HOMO and what is the LUMO of this orbit, this CO molecule? What is the HOMO? HOMO is the highest occupied molecular orbital. That is what sigma 2p2 is the HOMO, right? And what is the LUMO? Lowest unoccupied molecular orbital, that is pi star, right? This is LUMO. Okay, this is very important. What is the HOMO of carbonyl? Pi acid ligand carbonyl and LUMO of carbonyl. Okay, so this is the ligand we have taken. We know HOMO is sigma 2p z2 and LUMO is pi star 2p. See, this is HOMO and this is LUMO, right? This we have seen now. How this sigma 2pz2 will be forming? See, like this only bonding condition it will be, right? So this will join together, right? Positive lobes will join together. This is the way it is. Sigma 2pz2, sigma 2pz will be combining, right? This is what the molecular orbital is forming, right? So what will happen if it is bonded to any metal orbital? Metal orbital means d orbital, right? This is a doubly dumbbell shape, right? Positive and negative, and this carbon CO, right? CO, and this is the 2pz orbital. What will happen? This pi star orbital is here. This is the pi star orbital. So positive, negative, right? This is the CO molecule, okay? What will happen while it is bonding, metal carbonyls is forming? What will happen? This sigma electron density will flows to the metal. Then what will happen? Metal electron density will be increasing. So metal is having a tendency to decrease its electron density. What will happen then? Then metal is back donating these electrons to this pi star orbital, okay? This back donation is happening. So pi star is MD, right? Pi star is MD, 2px0, 2py0, both pi star orbitals are MD. So this extra metal electron density that will be receiving. Then again what will happen? Sigma 2pz will be donating the electron density to the metal. See, if you see like this back bonding will be there, that like we will say a term, technical term, synergic mechanism. So synergic mechanism. See, a ligand and a metal has bonded with a synergic mechanism. That ligand is called as pi acid ligand. So you know the mechanism of this back bonding or synergic mechanism. So two question possibility is there. How CO can act as a pi acid ligand? Pi acid ligand means HOMO will donate the electron and LUMO will accept the electron. This is the way CO will act as a pi acid ligand. And the second question is how CO can stabilize the low oxidation state of the metal. So how it is stabilizing low oxidation state means what it is low oxidation state? Low oxidation state means higher electron density, right? Higher electron density from where it is coming? From sigma 2pz only higher electron density is coming. So how CO will stabilize? CO will receive the electron. Pi star orbital of CO will receive the electron and stabilizes this. Another pi acid ligand I am writing C2H4. Okay, what is C2H4? CH2 double bond CH2, right? This is ethylene. We have seen what all are the, how many electrons are present, how many electrons it can donate? 2 electrons it can donate. One pi bond is there, so 2 electron it can donate. So Psi1 and Psi2 is the molecular orbital of C2H4, where we have seen while studying the pericyclic reaction we have seen, right? Psi1 and Psi2. In Psi1, in a ground state, Psi1 2 electrons are there, Psi2 no electrons, right? Molecular orbital in bonding condition both positive lobes and negative, and here it is pi star, then positive, negative, right? And negative, positive. This is the bonding condition and anti-bonding condition. This bonding condition means this will join together and this will join together, right? It will form like this, right? Bonding condition means it will be like this, combined together. So how it will become? It will act as a pi acid ligand. What will happen if it is joining with a metal? So this is the metal orbital. What will happen? This pi electrons, right? Pi electrons will be flowing into the metal, and the pi star orbital will be like this, right? Pi star orbital will be here, and pi star orbital will take back the pi star orbital will be receiving the electron density from the metal. Pi will be flowing into the metal, pi electron density to the metal, and from metal to pi star orbital will receive the electron density. This is the way it is back bonding to the metal. So C2H4 also, ethylene molecule also will act as a pi acid ligand. How many electrons it is giving? 2 electrons, right? So next example I will write allyl radical. If you see allyl radical, CH2 double bond CH, this is an allyl radical, right? It can act as a 2 electron donor. This pi bond it can donate, and here it is a 1 free radical also there. It can act as 2 electron donor or 3 electron donor. Both it can act. It will give 2 electrons or 3 electrons. How it will be? It will be bonded to metal like this also. From here it can bond to metal, okay? Then that will be a 2 electron donor, or else it can bonded like this to the metal. Okay, then it will be a 3 electron donor. This is the way it is bonding. This is what organometallic complexes are forming. I will be writing the set of the ligands, pi acid ligands, and how many number of electrons it will be donating to the metal, we will see. Another important term related to this topic is organometallic compound is 18 electron rule. What it is? 18 electron rule or EAN rule. What is 18 electron rule? With the metal ligand, if a compound is forming with metal and pi acid ligand, the metal should have a valency of 18 electron, then only that compounds will be stable. That is what 18 electron rule or effective atomic number rule we will say. So if it is a metal and a ligand is combining together to form a compound, this metal electron valency should be 18, then only that complex will be stable. That is what 18 electron rule. For that, predicting whether the complex is stable or not, and you should know how many outer electrons are present in the metal and how many electrons will be donated by the ligand. We will see the other ligands, how it will be donating. Okay, if you are seeing name of ligand, I am writing number of electrons donating by CO2, right? If it is, this will donate 2 electrons. All the ligands I am writing. Okay, this will donate 2 electrons. Dinitrogen complex, this will donate 2 electrons. If you see chlorine, bromine, iodine, all halogens, that will donate only 1 electron. If you see CH3, that will donate 1 electron. If you see CH2 double bond CH2, that will give CH2 double bond CH2 will give 2 electrons. Pi orbital, 2 electrons will be there, that it will be donating. Here I would like to refer one more time. Hapticity we will see. See, like this only metal is bonding to CH2 double bond CH2. How many carbon skeletons are in equal distance from the metal? That is what we will refer the term hapticity. What we will say? Hapticity. Hapticity is represented by the letter eta. Okay, here it is eta 2. Then I will write the example 1,3-butadiene. If you see 1,3-butadiene, it can bonded with the metal like this, right? Then the hapticity will be number of electrons donated will be 2. And if it is bonded to metal like this, then it will be 4. Hapticity will be 4. And the same way you can take benzene. If you are taking benzene ring, this is the benzene ring, right? It can either bonded like this, that is 2 electron donor, or else it can be a 4 electron donor, right? Or else it can be a 6 electron donor, right? This is 6 electron donor. This is the way this organic compounds will be bonding with the metal. So what is the number eta? Eta is can give 2, eta 3, eta 4. Based on that only you have to take how it has bonded to the metal. Okay, if it is a benzene, you cannot take blindly, it will give 6, not like that. If it has given eta 6 here, eta 6 means it is donating 6 electrons. If they are giving the ligand and giving eta 4, then it will give only 4 electrons. Based on that only you have to take, you have to choose your 18 electron rule. Okay, you will get a list of compounds and you have to find out whether the which one is the stable compound. Okay, clear? We have to find out these complexes are stable while calculating the valence electron. So we will calculate how the valence electron, whether it is obeying the 18 electron rule or not. First we will see CrCO6. Chromium is the metal. Chromium is having chromium. How many electrons, outer electrons are there? 6 electrons, right? From D block elements we have seen 4s1, 3d5. This is the electronic configuration of chromium, right? So 6 electrons are there, and CO we have seen from the list, it will donate 2 electrons. So how many COs are there? 6 into 2, right? Then it will be 12 electron. So 12 plus 6, how much you are getting? It is 18 electron. So this is a stable compound and it is obeying the 18 electron rule. The same way you have to find out for Fe, eta 5, C5, H5 twice. Iron is giving 8 electron, outer electrons 8, right? 4s2, 3d6. Then how many electrons are donated by C5, H5? 5. Hapticity is 5. So 5 electron it is donating. So eta 5, since it is eta 5, I am taking 5. 5 into 2. then how much it will be coming? 10. So 10 plus 8, it is also obeying 18 electron rule, correct? MoCO6, molybdenum, chromium, molybdenum, tungsten, right? So molybdenum also the same electronic configuration, 5s1, not 3d5, it is 4d5. So molybdenum is from the chromium, that group only, chromium, molybdenum, tungsten only. So molybdenum also having outer electrons, 6 electrons, right? 6 electron, and CO, 6 COs are there. Each CO will give you 2 electrons. So 6 into 2 is equal to 12 electron donor. So it will be 18 electron. This is obeying the 18 electron rule. Then the next is FeCO4 minus 2. Iron is having how many electrons? 8 electrons, right? Iron is 8 electrons and 4 COs. 4 COs will give there 4 into 2, 8 electrons you are getting, right? Then 8 plus 8, it will be 16 only. If you are seeing here one minus 2 charge is there, this minus 2 will give you 2 electron, right? So it will be plus 2 electron. So how much it will be coming? 18 electron. So this is the way you have to find out your complex, how much is the valency electrons are present. If you are getting the number 18, this complex is stable. This is what 18 electron rule. Other application of EAN rule is you can find out the number of metal bonds present in an organometallic compound. First one I am taking Fe3CO12. So 3 Fe's are there, right? 3 Fe's are there. Each Fe is donating 8 electrons. So 3 into 8 equal to 24 you will be having. Then CO, 12 COs are there. Each CO will be donating 2 electron. So 12 into 2 equal to 24, right? 24 plus 24 you will be getting 48 electrons, right? Is this 48 is a multiple of 18 electron? No, it is not a multiple. So what is the nearest 18 multiple? It is 54, right? 54 can be divided by 18. So what you have to do, if you are getting this number, the nearest 18 electron 18 multiple you have to see. So what you have to do, 54 minus 48 you have to do, you will be getting a value of 6. You will be getting 6. So you have to check with this Fe3CO12. How you will be getting the other 6 electron? See, if you are seeing Fe3, 3 iron atom is there. Each Fe bond will, each metal bond will give you 2 electrons. So here 6 is required. Here Fe3 is there, 3 Fe's. So 3 metal bond is there. 3 into 2 you will be getting 6. So you will be get a 18 electron multiple, right? So this is the way you have to find out the metal number. Okay, the next one is manganese, 2Mn, Mn2CO10, 2Mn. How many outer electrons are there in manganese? 7, right? So 2 into 7 equal to 14. CO, 10 COs are there, 10 CO, each CO is giving you 2 electron. So 2 into 10 is equal to 20. How much you have got now? 34. Which is the nearest 18 multiple? 36, right? So 36 minus 34 you are doing, you will be getting a value of 2. Okay, 2 means one metal bond is present. So Mn, this is that Mn2 is there. This is what metal bond will give you 2 electrons. So this will become 36 and it was a multiple of 18. So this is obeying the 18 electron rule, and you can find out the metal bond, one metal bond. Here how many metal bond? 3 metal bond. The next is CO4CO12. 4 COs are there, right? This CO and this CO, cobalt and other CO, don't get confused. Cobalt and carbonyl. This CO, how many electrons are there? 9, right? 9 into 4, right? 9 into 4 is equal to 36. And carbonyl, 12 carbonyls are there. 12 carbonyls will give you 24, right? So 60. What is the nearest 18 multiple? 72, right? 72 minus 60 you will be getting 12. 12 means 6 metal bonds are present, then only it will be, you will get 12, right? 6 metal bonds are present between CO4. So this is the way you have to find out the number of metal-metal bonds present. Clear? From the 18 electron rule, you can predict the metal-metal bonds present in a complex. Okay, and you can predict the stability of the metal. Hope you understand it well. Thank you for watching.